This talk will describe MegaFace, a universal representation for face recognition and quality assessment. Let's further introduce our motivations. The first part is about face qualities, and we present a few examples here. We can see that face qualities are affected by many factors, including describable image properties, describable face properties, and even indescribable properties. Current face quality models are usually based on labeled values. One drawback is that they lack a clear definition of qualities, as there are too many factors to consider and some factors are hard to quantify. In addition, they usually ignore the relationships between quality assessment and face recognition. In our work, quality is then defined as hardness for recognition and revealed by face magnitude. The second motivation is from face recognition. We found that current methods are quality agnostic and features are normalized for better performances. Moreover, they treat easy and hard samples equally, which makes noisy samples overweighted during training. The last one is about face clustering. Our work here has shown that knowing each feature's confidence for being class centers can benefit the task. Now the question is there a recognition model which can benefit all the three tasks? For quality, it can tell you whether a face image can be recognized. For recognition, it's done with noisy samples during training. For clustering, it can produce more reasonable distributions. Our goal now is to achieve a distribution in Figure A, where features from easy samples have large magnitudes but small cosine distances to class centers. Figure B shows that with such a distribution, feature magnitudes are positively related to cosine theta. If normalized, the features can further have a well-structured distribution. As a result, the direction can be used for recognition, the magnitude can represent quality, and the distribution can benefit the clustering. Let's now introduce details of our method. Here is the arcface loss and MegaFace loss. Denote the feature magnitude for sample I as AI. Compared to arcface, we may introduce two functions. The first one is M of AI, which produces magnitude aware margin, and the second one is G of AI, which encourages large magnitudes. Lambda G is used to balance the two items. The effects of the loss can be demonstrated by the figure, where pink area is the feasible region for a class and each circle means a sample here. Circle radius shows the feature variance, and the small radius means the high quality. Arcface only requires samples to lie inside the feasible region and leads to an unreasonable distribution. Figure B shows the least feasible region produced by M function, which assigns increasing margin with respect to AI. Figure C shows that features are pushed away by a G function, while restricted inside the feasible region. We use an example to demonstrate the joint effects. Suppose a container with the same shape of the feasible region and there are two balls with different radiuses. Because of the gravity G, the two balls drop to the container and are located differently in the end. Therefore, we will have the desirable distributions in Figure D, where these samples are close to class centers while away from the origin. We require several constraints on MG and lambda in MegaFace, then we can mathematically prove the two properties. The first one states that the Li is a strict convex function of AI and has a unique optimum. The second one says that the optimum is monotonically increasing as the hardness of recognition decreases. Please refer to the paper for proofs. Here we present the plot of feature magnitudes and hardness for recognition. Besides poor performance, softmax does not have a clear correlation. In arcface, a lower bound exists and the magnitudes from easy samples have very large variances, while in MegaFace, a strong positive relationship can be observed. These slides present a few more visualizations. In Figure A, we can see that faces with larger magnitudes can create more clear mean faces. Figure B presents a few face examples and the distributions of feature magnitudes on 4 benchmarks. Figure C shows that cluster centers tend to have large feature magnitudes, which can be utilized in the clustering task. We further present some quantitative results. For recognition, MegaFace achieves performance boosts compared to current recognition methods. For quality assessment, the predicted qualities can have better results than current state-of-the-art quality models. For clustering, results from 4 algorithms show that the distribution of MegaFace is more suitable for the task compared to arcface. Thank you for listening. Please find the paper, codes, and more detailed talk in those links.